Hello everyone. So in this example I want to look at how we can connect the Gibbs energy, specifically the standard Gibbs energy, to the equilibrium constant, right? So the standard Gibbs energy of reaction is connected to the equilibrium constant, right? Because that gives us indication A, whether or not an equilibrium is product or reactant favoring or a perfect equilibrium. And so we can also calculate the equilibrium constant from that quantity. So the example specifically says, consider the equilibrium at exactly 25 degrees Celsius, right? And then there's some equilibrium of ethane with water gas giving, ethanol. And we're given the standard Gibbs energy of reaction. Okay, and then it says, calculate Kp for this equilibrium. And also comment on the sign of the standard Gibbs energy of reaction and the magnitude of this Kp. So this is a straightforward calculation and then some discussion. And I actually like the discussion more than the calculation part, so let's just get into it. So how can we calculate Kp from the standard Gibbs energy of reaction? Well, there's an equation. So Kp is equal to negative e to the power negative delta Rg naught divided by Rt. And I like to put my standard state as the pinmole. Yeah, that's what that thing is called, but okay. Alright, so just to make it a bit easier to write, I'm going to write it as exponent, exp, so exponent. And what is the exponent to? So it's negative. And then there's some stuff that we put in the exponent. So the first thing that we put in the exponent is, of course, the g. And what is delta Rg naught value? Well, we're given it as minus 14.3 kilojoules. So let's make that joule. So times 10 to the power 3 joule per mole reaction. All right. So we're given that, and we must divide that by RT. So 8.3145 joule per Kelvin per mole reaction. This is the only time you're actually allowed just to ignore this whole mole reaction thing. You're actually always just allowed to ignore it, but I'm a difficult person, so that's why you're not allowed to ignore it. And then of course the temperature, we're at 25 degrees Celsius, exactly. So 298.15 Kelvin, right? That's 273.15 plus 25 degrees Celsius gives us the Kelvin temperature. All right, and that is the exponent. So you take e to the power minus that fraction. All right, and technically those minuses will cancel, so it's e to the power plus all these things. All right, and the value that I get here is 320.066, etc. And then further than that, if you round this, you get 320. All right, three significant figures, yeah, 14.3, so 14.3, three significant figures. That's what we get. So now let's comment on the sign and the magnitude. So if we look at the sign of delta Rg naught, right, we see it's negative. So that would imply to us that we had a product favoring equilibrium. But this is also supported by what quantity now? So this is supported by our Kp being larger than 1. It's not much larger than 1, but also our delta Rg naught is not like excessively less than 0. By Kp being larger than 1, which also suggests also indicates, right? When Kp is larger than 1 or much larger than 1, what does it mean? Which also indicates a product favoring equilibrium. All right. So both the K and the Gibbs energy of reaction, standard Gibbs energy of reaction, indicate in this case that it's a product favoring equilibrium, right? And that's how you can calculate one from the other. Of course, how you can calculate Kp from the Gibbs energy is, of course, you can take the ln and then you can solve for the Gibbs energy. All right, cool. So that's this little short example, done and dusted, and the interpretation of it. Right, I'll see you in the next video. Thank you for watching.